Testing. There we go. Okay. Why does my mic keep cutting out? Test. Oh, there we go. That was weird. We might have a small handful of you out there. But we're gonna go ahead and start our Geometry 5.4 notes. Turn on the volume just a wee bit. Good. So right about here, we will begin our 5.4 notes. We're concluding Unit 5 for Geometry. Well done to us. This is our last unit. We're going to have some things going on that are going to interrupt our flow a little bit, and this is really the last bit. Well, maybe I shouldn't say the last bit, but practically the last bit of new content. So 5.4. Let's take a look. We're looking at proofs again. We looked briefly at proofs, and if I could, let me just give you a quick reminder that a proof has a beginning and an end. The beginning are the ingredients needed, right? But in the end, we're trying to prove a statement, right? So we know some things. We know some things, but we don't know. But we're trying to prove this end statement, right? Take a few of these ingredients, mix them together, and prove to me, show me evidence as to why this statement is true. Hi, I just did the 5.3 and I got 11 out of 15, but I had all of them right. Why did I mark them wrong then? If it was right, what was the situation? So what we're doing here is what have we discussed in the past about parallelograms? We've discussed pretty thoroughly that for parallelograms, the opposite sides are congruent. Okay. That's what this statement says right here, right? AB is congruent to CD, and that AD is congruent to CB. We know that to be true, okay? However, why is it true? It's kind of a fact that we've all been assuming, right? We haven't really proved it very concretely. You know what I mean? Right? It's like, that'd be like me just casually telling you, well, all the angles of a quadrilateral is 360, right? You believe me, we know that to be true, but why is that true? Well, opposite sides of a parallelogram are congruent, right? Yeah. You believe me, I believe me, but why is it true? We're going to prove why it's true right now, okay? So we are given a parallelogram. So we know that. So let's look at this proof step by step. So number one, ABCD is a parallelogram. Well, that was given to us, right? That was given to us. Lovely. Draw DB. Okay, let's draw D to B. If it'll be straight for me. Let's draw D to B. There we go. So we drew D to B. Why can we draw D to B? Well, number one, it just makes sense, right? Of course we can draw a line, but the formal way to write that is between any 2 points there exists a line or segment, whatever you want to call it, okay? So there's that. AB is parallel to DC, and AD is parallel to BC. Why is that true? What is the reason, right? This is the fact, and this is the reason why that fact is true. Why is that true? Well, that's the definition of a parallelogram. Whoops. That's the definition of a parallelogram, okay? All those other facts that we've named, opposite angles congruent, opposite sides congruent, the diagonals bisect, those are just things that happen to be true. But fundamentally, why is a parallelogram a parallelogram? Because the sides are parallel. That's the definition of a parallelogram. Okay, the next statement says ADB is congruent to CBD, and ABD is congruent to CDB. Said that 4 of them weren't worth any points, so I didn't get points for those, but they had a green mark on them. Roger that. Okay. What's your name? So, why is that true? Why is that true? Well, we've actually discussed this before. Why is this true? Well, what did we just say beforehand? That these lines are parallel, and this is a transversal. We've discussed how these pink angles are alternate interior. Okay, we've discussed that, okay? Because they're in between the parallel lines and on opposite sides. So, that's an alternate interior angle. And so are the orange angles, right? We're in between those sides and we're on opposite sides. So they're alternate interior angles. Roger that. Gotcha. So those are alternate interior angles. This is the reflexive property. You might have remembered that. That might jog a ring a bell. That reflexive property. That's what we say when something's congruent to itself. So what have we done here? You're not going to be doing this proof on your own, right? By any means, right? That's why we're doing it together. What have we come up with here? ABD is congruent to CDB. We just said that this triangle is congruent to the bottom triangle, which we knew that to be true, right? Because it's a rotation. That's something that we kind of already knew, but we just proved them congruent by angle, side, angle. You remember those? Do you remember those? Angle, side, angle. That's angle, side, angle. And lastly, because we've proved these two triangles congruent, we can say that this side is congruent to that side, and this side is congruent to that side by CPCTC. So let's kind of recap the logic behind this, because I don't expect every single one of us to just be able to whip this out, but I want you to understand why we did this and like what the strategy was. So we were just given a random parallelogram, and our strategy here was, well, if I can split this into two triangles, if those two triangles are congruent, then I'll know that the pieces that match up are congruent, right? That's something that we know, right? If my left hand is congruent to my right hand, well, my left thumb and my right thumb ought to have the same length, right? If my hands are identical, that means the individual parts about my hand should be identical, right? That's kind of the logic. So if the top and bottom triangles are the same, well, then the sides of that triangle should also be the same, right? So that was the logic, right? Prove the two big things congruent, so that way we can isolate and say, oh, well, the sides are congruent. That's the logic there. Okay, so we're gonna do something similar here, okay? Look, you can see all of the statements that are already written for us. We're once again going to prove triangles congruent, AED and CEB, right? We're kind of spoiling what's about to happen, and that's okay, right? I think that can benefit us, okay? So if we can prove these triangles congruent, that's going to help us in the end, and you'll see why here. So what are we trying to prove? We're trying to prove that the diagonals bisect each other. You see that? That's another fact that we already know, but we're trying to prove it, right? We're trying to show that this half is the same as that half. We're trying to prove that this half is the same as that half. That's what this says. Well, if you think about it, right, if I can prove that this triangle is the same as this one, well, this leg and this leg ought to be the same. So, oh yeah, then that means the diagonal has been split in half. If both sides are the same length, that's the definition of being split in half. Well, the reason why this side would be the same as this one is if the triangles are congruent. Okay, so let's clean this up here because we don't know that yet, right? We're trying to prove that. So why do we know that AD is congruent to BC? Well, we proved it up top. See previous proof, right? We proved opposite sides congruent. We just did that up there. That's why it's true. So I'm going to roll with it, right? I'm just going to roll with it. AD is parallel to BC. Well, that's the definition of a parallelogram. The sides have to be parallel for a parallelogram. Once again here, DAC and BAC. Well, once again, DAC and BCA. That's our alternate interior angle situation. And AED and CEB, what are those? You should know what those are. Those are vertical angles. And we just proved these triangles congruent. There are 4 options: SSS, SAS, angle side, and angle side angle. Which one did we just have? We have a side and 2 angles. So this one's out and this one's out because we have 2 angles. Well, are those angles in a row, or is the side between the angles? Angle followed by another angle and then the side. So that's right, it's AAS. Well, if this triangle is the same, let me erase and just sort of highlight it. If this triangle is the same as this one, it's not a reflection, mind you. It's not a reflection, right? What we've shown is that this angle is the same as this one down there, right? So it's not a flip, it's a turn. So this angle rotates to here, and this side rotates to this side. So that's why this side's congruent to that side, right? So we've just proven that those sides are congruent. And why is that? CPCTC. Those are the corresponding parts. When you look at these 2 triangles, this side matches up with this one, right? This side matches up with this one. All right, last one here. This is specifically for a rectangle, not just a parallelogram, but for a rectangle. So, we know a few more things about a rectangle, okay? Remember, So I said this in class, I think for just about everybody, something along these lines. A parallelogram is something that has parallel sides. That's the one fundamental fact. A rectangle is a four-sided shape that has all angles that are the same. That's the one thing that we know, right? That is what makes a rectangle, is that we have 90-degree angles everywhere. 90, 90, 90, 90. And that adds up to 360. And a rhombus, as just a reminder, is something that has all four sides the same. So a parallelogram, the sides are parallel, but nothing specific about the angles or the lengths. For a rectangle, yes, the sides are parallel, but specifically the angles are identical. Not necessarily true for a parallelogram. And for a rhombus, yes, the sides are parallel, but those sides are the exact same length. Nothing specific about the angles, just the sides. So that's the one fundamental thing. Why am I bringing that up? Well, it says right here, C and D are right angles. Why do we know that? Because that's the definition of a rectangle. That's what makes a rectangle, is that we have 90-degree angles everywhere. So now we know that C is congruent to D, right? If C and D are both right angles, that means they're both 90, meaning they are congruent. So these two guys are congruent. AD is congruent to BC. Well, that goes back to, again, what we've proven is that opposite sides are congruent. We've already shown that to be true, right? So that's why that's true. Look at what we're trying to go for, by the way. I probably should have pointed that out before I started. We're trying to prove that the diagonals are the exact same length. In the previous problem, we were trying to show how the diagonal had been split in half, but we did not show that this whole thing was congruent to this, because that just wasn't true. But here, we're trying to show, we've already proven that we can split it in half, right? I could do the exact same proof on this rectangle as this parallelogram, right? And I could prove to you that this side is congruent to that side and this side is congruent to that one. We could sit here and do that all over again, but I don't want to, right? We're going to be more specific. We're trying to prove that this entire thing is identical to this. That's our mission. The reflexive property, what do you think we're going for there? Do you see what maybe see what we're going for here with ADC and BCD? ADC is this triangle and BCD is that triangle. We have a side, we have an angle. And remember, how do we prove triangles congruent? SAS, SSS, ASA, AAS. We have a side, we have an angle, and they share this bottom side. You realize that? This triangle and this triangle share the bottom side. So with that being said, these two triangles are congruent. Actually, let me switch up the color. Actually, let me fill it in. These triangles are congruent. Yeah? By SAS. And if that's true, if those triangles are congruent, then that means their hypotenuses are congruent to one another. And those hypotenuses, hypotenuse, are the diagonals. Voila. You'll notice all three proofs used triangles. And that kind of comes back down to what you and we've already done together as I rotate things on GeoGebra and prove to you, like, and well, show to you, maybe I shouldn't call it a proof, but like I visually prove, so to speak, how these triangles can be manipulated to create these shapes. And that's kind of what we're getting at here with these proofs, is that, oh, we are recognizing these triangles, and it's like if we can prove triangles congruent, well, then a lot of these nitty-gritty pieces we can also prove. You know, not only can we say this, right? By proving these two triangles congruent, we can say more than that, right? We can say that this angle is the same as this angle now, right? Because these triangles are exact carbon copies of each other. So this angle is the same as that one, and this side's the same as that, right? It's all of these things are true, and this angle is the same as that one, right? All of this things, it's like a trickle down effect, right? If all of these triangles are congruent, because the top is congruent to the bottom too, right? And the left is congruent to the right, all of these things, everything starts to match up. It's real nice. All right. So, I need to make an announcement for Algebra 2 because there's that for geometry. We're good to go. Let me turn on my fan. Ooh, the fan feels good. All right. Let's do Algebra 2. Shall we? All right, right about here is the start of the Algebra 2 notes. We're looking at Unit 5, Lesson 1. All right. So, an exponential function. You've probably heard this, like, oh, it grew exponentially. It grew a lot, right? Lots of people, when they think exponential, they think it just shoots up, right? You know, if you were to imagine a graph, it just spikes and shoots straight up. That's exactly right. That's an exponential function, okay? So we're looking at the graphs of exponential functions today, and you guessed it, a lot of the same stuff is true. So, when you've got something that is bigger than 1, it stretches. When you got something that's less than 1, it shrinks. When you have a negative, it flips. Okay? When you have something that is minus h, it goes to the right. When you have plus h, it goes to the left. When you have something that says plus k, you go up. When you have something that says minus k, you go down. We've seen these things. We love these things. We're pretty used to this. Okay? So, when does our function grow? There's a new number in town. It's this b value, right? Well, that determines whether we have growth or not. When that number is bigger than 1, we're going to get bigger, like so. And our graph is going to look something like that. When we have a number between 0 and 1, aka less than 1 essentially, we're going to decay downwards like so. The asymptote of the graph is a barrier, right? An asymptote is like a barrier, okay? And what do I mean by that? Well, you can see that this function starts to bottom out. This function gets closer and closer and closer to a specific number, but it will never cross, right? This does not go forever down. This actually starts to bottom out and level out, okay? And that barrier, that line, is called the asymptote. The asymptote will always, always, always take the form y equals k, our vertical shift. So when you shift something up 1, you've just moved the asymptote to y equals 1, a horizontal line at 1. It'll never cross below 1. When you shift it down 2, you've just made a vertical asymptote that is down, a horizontal asymptote that is at -2. The graph will never cross -2. So take a quick peek at these pre-graphed things. Stretch, right 4, up 5, and that's bigger than 1, so it's a growth. And you can see here that the horizontal asymptote is at 5. That's the k value. All right. You can see that this thing was moved 1, 2, 3, 4, right 4. And by right 4, it's kind of hard to tell where quite exactly this movement occurred, but you can kind of see that the graph starts to take off at about right there, right? There's a slight curve and then it just starts to go straight up from there. Again, we've never been quite 100% exact with our graphs, and we're not going to start now. But that's kind of the vibe, is that, you know, it just really starts to take off right around there, okay? The stretch is a little less obvious in this case. Don't be too overwhelmed with that. And the 3 just, again, means that it's a growth. We're not trying to get too complicated here. So we moved down 5, and so now the asymptote is at -5. The graph's getting, it looks like it's practically on -5, and that's just due to the way how close it is. But technically speaking, it'll never cross below -5. Why is this going down in the first place? That's because this is a decay. It's less than 1. All these numbers mean the numbers that we're used to. Please do not think that graphing this or looking at these graphs is any more complicated than we've seen before. These numbers all play the same role. And this number, don't stress about it. Just know that when it's small, when it's less than 1, when it's a fraction, it's going to go down. When it's bigger than 1, when it's this big number, it's going to go up. So that's kind of the gist here. And again, the 2's a little less obvious. And the left 4 situation, again, 1, 2, 3, 4, you can just kind of tell that it, like, again, it just kind of shoots up from there, right? And starts to bottom out from there. Okay, not stressing. So, real quick, let's just figure out whether this is growth, decay, or neither. The B value determines whether it's growth, decay, or neither. So you look at this B value and you say, well, that is less than 1, so therefore decay. You look at this B value and you say, oh, that's greater than 1, so growth. You look at this B value and you say, oh, that's greater than 1. That's growth. You look at this B value. Oh, I overlooked something. Ooh. Shh. I overlooked something. My apologies. Do you see what I overlooked? These are both right. But what did I slightly overlook? Right there, that negative. Does anyone remember what a negative exponent tells you to do? It tells you to take the reciprocal. 5 to the -1 is the same thing as 1/5. So right here, we're actually looking at that. This is equal to that due to the negative. So this is less than 1. So therefore, decay. And check this out. This negative here, that negative there, what is that doing? That's taking what was a growth and flipping it, right? In the math world, we don't call that a decay. We call this a decay, where it starts to flatline. That is decay. This, yes, in our everyday language, we might consider that a decay because it's getting smaller. However, it's not flatlining. So in the math world, we don't consider that a decay. Okay, we are just going to call that neither. All right. So obviously look at this number first, but negatives are gonna mess with you. Negatives mess with us, okay? And I encourage you to plot it into Desmos, right? I mean, I say that all the time, right? If you just plug this into Desmos, you're gonna see a graph that goes, right? If you plug this into Desmos, you're gonna see a graph that goes, okay? Plug it into Desmos, and you'll also be able to tell whether it's a growth or decay. So let's do a few quick plots by hand just to kind of get the feel for this. Let's do the complicated looking ones, okay? I'm going to skip those first two. If we need more examples in class or something, I'll do those. But I think doing 2 right here should be sufficient, right? So this right here is our horizontal asymptote. I immediately know that. Okay? I immediately know that. This asks for a y-intercept. A y-intercept is where it crosses the y-axis, right? Or in other words, when x is 0. When x is 0. So plug in 0 and you'll get your y-intercept. So 0 plus 3 is 3. 4 to the third. 4 to the third is 64. 64 divided by 2 is 32. And 32 minus 3 is 29. One more time. 0 plus 3 is 3. 4 to the third is 64. 64 divided by 2 is 32. And 32 minus 3 is 29. So way up here is our y-intercept. This is a growth function, right? So I'm not going to be too crazy, right? Boom. I'm not going to be crazy. There it is, right? When it comes to our online assignments, you're just going to have to pick the right graph anyway. So I'm not going to get crazy. There it is. We are going to need to be able to state the domain and range, though, which Desmos is not going to tell you. So domain is x values. In this case, all reals, right? This thing goes forever to the left and forever to the right. It goes up, but it's still working its way right ever so slightly. It's just really quick. But eventually it's going to be clear over here, right? It's just going to be really high. The range, however, is not infinite. Why? Because of this asymptote. That's as far as it's going to go. Is it going to touch that? No, it's not going to touch -3. And it's going to grow up from there. So it's not going to touch it, parenthesis, and it just goes up from there. We could also write this as it'll just be greater than -3, right? The y values are all bigger than -3. That's another way to write it. End behavior, right? We've taken a look at this before when it came to our cube graphs and our our parabolas and stuff. It goes up, down, that sort of thing, right? You remember that? So in this case, as we go to the left, what are we getting really, really close to? Y is getting really close to -3. And as we go to the right, where is y going? Up. We find the y-intercept just because it's an easy point to find. There's nothing like incredibly profound about the y-intercept other than it's like this nice easy point to find, so I can kind of get a feel for my graph, right? If you didn't know that the graph was going to shoot up all the way, you might have been tempted to draw a graph like that. And that is just straight up wrong because the graph has got to be way up here, right? It's not going to cross the y-axis all the way down at 4, right? By finding the y-intercept, we realized that it was rising super quickly. And we can do the same thing here. This is going to be a decay though, right? So let's see what happens here. -2/3 raised to the 0 minus 2 plus 1. Ooh, this one's cheeky. A little cheeky here. So -2/3 raised to the -2. Well, that flips it and makes it 9/4. Because 3 squared is 9, 2 squared is 4, but I flip it. So -9/4 plus 1 is -5/4. So our y-intercept is down here. Our horizontal asymptote? Again, it's always just k, right? Those are going to be some of the easiest questions on the classwork. What is the horizontal asymptote of the given graph? Boom, whatever number staring you in the face right there. Okay. So our graph is decaying, right? So it should look like this, right? If it's decaying, shouldn't it flatline and bottom out? It got flipped, which is why it actually looks like this. True story. There's our graph, right? It should have looked like this, but it got flipped. Our domain, of course, all reals. It goes forever left, forever right. That's always going to happen, right? Range is the thing that gets limited by the asymptote. So how small are we going to get? Clear down at negative infinity. This thing keeps going down, 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 down. But it's not going to get any higher and will never touch 1. Same thing here, right? As I go to the left, this thing goes down, 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 down. And as I go to the right, this thing gets pretty darn close to 1. This is a quick little rework here. Our exponent properties. Our exponent properties say that if you have two things multiplying together in your exponent, that's the same thing as an exponent raised to an exponent. We merge these together by multiplying. We've seen this property once before. I showed you two properties in the past. I showed you this. If I have a to the b times a to the c, we can simply add the exponents. But if I have a to the b to the c, then we're multiplying the exponents. Well, that property can be kind of useful for us because this exponent looks a little odd. In the grand scheme of my shifting and whatnot, I know that this is going to be a growth because 3 is bigger than 1, but we've never seen a number out in front of the x like that before, right? We always have a left and a right shift, x minus something, x plus something. We never had a number out in front of the x like that, and we don't plan on it. So what we're going to do here is rewrite this as 3 to the third to the x. What's 3 to the third? 27. And that is something we can handle, right? Here it's just like, whoa, big time growth. Big time growth function. Here, that kind of gets lost on us, right? I think this is more profound and easier to analyze than this, right? And that's why we're choosing to rewrite it. Same thing here. This is going to be 16 to the x. 4 squared is 16, then raised to the x power. There's something in mathematics called the natural number or Euler's number or whatever you want to call it. It's this letter E. You might have seen it before. The letter E is called Euler's number, or some people say Euler's number, but that's wrong. It's the natural base E. And it's a number, 2.1 something, 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 something. I don't know what it is. I used to know, but I don't know it anymore. It's sort of like pi, right? This weird random number that's just like really important. That's what E is. And it gets used a lot, especially in some upper level mathematics. So if any of you are at all engineering inclined or physics inclined, and that you think that's like a profession that you might want to go in, the natural base E is pretty common. So what we're looking at here is a graph where the base is E. Now, again, E is a number that is bigger than 1. Right there, right? So therefore, that's going to be growth. Right? If I have e to the x, I instantly know that that's growth. Okay? I mean, unless, slap a negative in front of it. Obviously, those other rules apply. Don't get me wrong. But, at its core, e to the blah, blah, blah is going to imply a base. A growth. But as far as our analyzation is concerned, like all of this stuff is the same, right? It's just e is this like super special number. But I just want you to think of it as a number bigger than 1. So therefore, growth. Don't overcomplicate it. So when you look at this domain and range and whatnot, I mean, nothing's changed. Like literally nothing's changed. Like what? I don't even know. Why do we even bother doing it, right? You know what I mean? I'm just going to do 1 because who cares, right? Nothing's changed. So domain here is all reals, of course, right? Forever to the left, forever to the right. Our horizontal asymptote is at -4. You can see it gets really close to -4. Awesome. So our range is from -4 all the way up to infinity. And our end behavior, as we go to the left, that's when we're getting close to that -4. And as we go to the right, that's where we're going up, 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 up. And there it is. I'm not going to bother doing another one. You can see here that, take a look at that. This became a decay because of the negative exponent. That's it. You can plug E into Desmos and it will understand it completely. I've done it before. And if you can't get it to work, well then just ask me. Let's look at the word problems, and that's how we're going to end it. Word problems with exponents is probably our most, might I say, realistic word problems, if you know what I mean, right? I know some of you might be like, it seems a little off the wall. I think exponents is a pretty relevant word. Some of these word problems might feel like they're like sort of random still, but in general, there's lots of solving that you can do in the real world with exponents, stuff with like finance and stock market and populations, especially in like biology with like cells and bacteria and stuff like that. The growth, the reproduction, so to speak, of the bacteria or the spread of viruses, aka coronavirus, right, can be exponential. Lots of pretty relevant things that can be modeled by exponential growth, or in the case of dying of species, exponential decay, stuff like that. Things can be modeled pretty easily with exponential functions. So from 1991 through 1995, the number of computers, C, per 100 people worldwide can be modeled by this, okay? So, let me just plug this in to Desmos. Why not, right? Why not? Why not? So here is the exponential function. And basically what we're saying is as time goes by, people are getting more computers, which makes sense, right? Because this model started in 1991. Probably not a lot of people had computers in 1991. That was kind of the spark of the internet, right? That, we were starting to get to the year 2000, right? When things were really booming and everyone started to have a computer in their home. So as the years progress, even just 10 years in the future, the growth of people having computers grew exponentially. Yeah, my chat is white against this. It is what it is. It's because it's Desmos. I should probably change the font, maybe the font color. So it started to grow exponentially, obviously, right? Lots of people getting computers. So if we go back, identify the initial amount, the growth factor, and the annual percent increase. Okay, so let's go one by one. The initial amount. The initial amount of computers. Well, I would call that at time 0, right? When no time has passed, that's how many people first had computers. And then as time progresses, 1 year goes by, 2 years go by, we'll know how many computers exist at that point in time. But if we want the initial amount, we want time to be 0, aka 0 years have passed. Anything raised, 1.5, not 2.5. Oh, I typed that wrong into Desmos. Whoops. I'll fix that for us here. So, anything raised to the 0 power is equal to 1. So, boom, 25.2 computers, which I know sounds silly, but that was per 100 people. So that was the initial amount of computers. What is the growth factor? Well, the growth factor is the number 1.15, right? That's the number at which things are growing, right? That was a dumb sentence. That's the number that tells us things are growing, right? That's the number that tells us things because it's bigger than 1. So the growth factor is 1.15. The annual percent increase. Well, this is the percentage, right? By multiplying something by 0.15, you're taking 15%, okay? And if you didn't know that, right, spoiler alert, that's how decimals work, right? If you want to take 15% of something, you multiply it by 0.15 because that's the decimal version. If you want to take 25% off, right, a discount at the store, that's 0.25. So multiplying something by 1 over and over is not going to make it any bigger, but multiply it by 1.15, you're making it 15% bigger over and over and over. All right, so estimate the number of computers per 100 people worldwide in the year 2000. Well, if this function helps you find out the number of computers, we just basically need to know in the year 2000 how many years have passed. 92, 93, 94, 95, 96, 97, 98, 99, 2000. So in 9 years, how many computers are there? Well, T is 9. Figure it out. Plug it in, right? Use a calculator if you have to. I'm going to use Desmos as my calculator. And by that, I mean, let's make this a table. So in 1 year, in 2 years, in 3 years, in 4 years, in 5 years, in 6 years, in 7, 8, 9, there were 88.65 computers per 100 people in 9 years, aka the year 2000. So in the year 1992, 93, 94, 95, 96, 97, 98, 99. In the year 2000, there were 88.65. Pretty easy. The number of newly reported cases of tuberculosis. So again, here's what I was talking about, like with diseases. In the United States, from 1991 to 1996 can be modeled by the approximated can be approximated by the equation blah, where t represents the number of years since 1990. Identify the initial amount, the decay factor, and the annual percent decrease. The annual percent decrease. So the initial amount, spoiler alert, is again this big number out in front. Why is that true again, right? Because that's what happened over here, right? Why is that true? Well, because when you plug in 0, you're making this a 1, and 1 times anything is whatever that is, right? So we're basically canceling this out. Nothing's happening, right? The only reason this is here is to help simulate time passing, but we don't want any time to have passed, right? We want the initial amount, 28,500. So the decay factor is the number itself. However, we have to be a little more clever here with our percent decrease. It is not decreasing by 95%. That is not true. Okay? We could just look at this decimal and say that it was an increase. Because, well, think of the number 1. Here's the number 1. 0.15 is just a wee bit ahead. Well, I guess my webcam flipped. Just a wee bit ahead. It's 15% ahead. 0.9567 is not 95% decreased, right? That'd be practically zeroing it out. So this is only a wee bit smaller than 1. How much smaller? How much smaller? .33%, right? You see what I did there? The distance away from 1, right? This was 0.15 above 1. This is 0.043 below 1. That's how much it has been decreased. Not 95%, okay? That's way too big, right? This is much closer to 1. 95%, that'd be way down low, right? Multiplying something by 0.9567 is not 95% change. Okay, so 4.33%. In what year was the number of newly reported cases in the United States approximately 25,000? So when will our cases be 25,000? Well, we don't know which time. So we're actually solving for t, right? We don't know the year, right? That's actually what we're solving for. But what we do know is that the number of cases is 25,000. So in what year will we make this occur? We're actually going to solve this equation. Okay? We're solving this equation. How do we do that? Well, let's try to get t on its own, right? Let's think about that. How do we get t on its own? Divide by 28,500. We can try that out. 0.9567 equals to the t equals, what is that? When I plug that into a calculator, actually, let's just leave it as a fraction right now. How do I get the t out of the exponent, right? It's kind of weird, right? I can't just divide this away. This is not multiplication. That's an exponent. Do I take like the... We're on a bit of a hang up there. We're going to save this for later. We're going to save this for later, all right? Let's estimate it. Let's try to guess, quote unquote, guess when that occurs, all right? Sort of like question C. Estimate the number of newly reported cases on 2015. Well, I guess it's not like C. I kind of spoke too soon there. Sorry. We're going to kind of guess, okay? And by guess, I mean we're going to use Desmos. So here's our graph. Look, the tuberculosis cases are dropping drastically as time goes by, right? There's like practically no tuberculosis cases anymore nowadays, I'm pretty sure. So it has decayed by quite an amount. So when did it hit 25,000? Well, let's kind of guess. After 1 year, it dropped to that. After 2, after 3, after 4, after 5, after 6, after 7. Check that out. So somewhere between 2 and 3 years, it hit 25,000. You see what I'm getting at there? You see that? I can't even see the points. They're so high up, so I'm not even going to bother. So after 1 year, the cases dropped from 28,500 to here. After 2 years, to here. After 3 years, to here. So some right before 3. I'm going to say about 3 years. In what year? So it took about 3 years, aka it was the year 1994. And this says estimate the number of cases in 2015. Well, that means we know how much time has passed. We know what T is. What is T? 2015. Well, from 91 to 2001, that's 10 years. And then 2011, that's 20 years. So 2012, 2013, 2014, 2015, that's 24 years. So what happens in 24 years? Let's check it out. Clear down to 9,850 cases. 9,850 cases. And that's what I'm going to write. And that's what I'm going to do. Honestly, but I saved these word problems for class because I'm getting a little tired. This is getting a little long. I don't think we need to see this many in the video, and maybe seeing them a little bit later in class will be more beneficial. So we'll pause there and we'll utilize these for class, okay? So with that being said, not too many people showed up live, but hopefully we get some replay views. Thank you for tuning in. That's 5.1. I'll catch you in class.